thanks for the introduction. Thanks for having me. So I'm with Effekte. My name is Eberhard. Effekte is a software company, so we do a lot of projects, about 120 people throughout Germany and Switzerland. Mostly development work. I'm sort of a special guy, that's why it says fellow there. So I mostly do trainings, consultings, and presentations, and these kinds of things. What I did do in the past is I wrote a few books. So here are my books about continuous delivery. That one has been translated into English. Same thing for my microservices book. And there is a short introduction about microservices, which is this one. And that's actually free, so you can download it at the URLs. At the end, I will show you how you can get the slides, so feel free to download that stuff. And this is my new book. It is the English translation is available and it's complete, but it's being polished right now. So this one talks about how to do microservices in practice. So it's a technology book, gives a lot of very concrete examples, and it also invites you to do your own experiments and your own extensions to those examples. Those examples are all on GitHub. And if you're interested, there is also this one, which is a short version that talks about a few of the examples, and that one again is free. So what I am going to talk about today is how to implement microservices, and it's going to be a rather technical talk, so I will talk about a few technologies that you can use to do that, to implement microservices. And I am going to talk about what are microservices. So that might seem to be a little bit boring, because nowadays everybody knows what microservices are, but I do have a different point of view, I guess. So what we came up with to get a better understanding about what microservices are and to give some best practices is this independent systems architecture. So first of all, we changed the name, so we are focusing on independence. This is really what I think what microservices are about. And what I am going to talk about is, for the next few slides, is these principles in a very brief format. If you're interested in it, there is the link at the top. Here's isa-principles.org, so you can get this presentation there. There is a more extensive presentation actually that contains a lot more slides, and you get all the principles there. Why did we do ISA? Because we thought that it might be worthwhile to say what microservices really are, how they're meant to be, and to get an understanding of that. So first, it's in its principles. First of all, there is the principle that microservices are modules, so they are part of the system, and they are just another way to do modules, much like Java packages, classes, namespaces, all these kinds of things. What sets them apart is that the modules are implemented as typically Docker containers, so you can deploy them individually. And that is quite different, of course, from Java namespaces or whatever. So it's a different way of doing modules. And because they are so flexible, and because you can have a different technology in each microservice, you need to have some standards. I would argue if you want to build a system that consists of modules, you still have to have something that actually makes the system a system. So for example, all the modules must talk to one another. That's where micro and macro architecture comes in. So the macro architecture are standards for all microservices, like the communication, while the micro architecture is about things that can be done differently in each microservice. So for example, you could have a different implementation in every microservice. So you could have one in Java, the other one in PHP, and what have you. So that's a principle. Then there is the idea that you need to standardize integration because they need to talk to one another. So somehow you need to make sure that they can actually talk to one another. And you should probably also define the technical needs, not just how they are integrated, whether they do synchronous or asynchronous communication, but also how you do it on a technical level, whether you do it with REST or messaging or what have you. So those two principles are actually examples of the macro architecture.
Then the continuous delivery pipelines should be independent, because otherwise you can't really deploy those microservices independently. And then the question is, why do you even use microservices if you don't get that benefit of independent delivery into production? So that is why I advocate using separated continuous delivery pipelines. You should probably standardize operations, because otherwise there is a huge number of microservices and they are all operated differently, and that's a lot of effort, so probably you don't want to do that. You want to standardize that, and that's part of the macro architecture. But the standard should only be on the interface level. It doesn't make a lot of sense to say, yeah, please use this library to do the metrics. It's much more sensible to say, this is how you should present your metrics, and I don't care how you implement that, because in the long run you might have microservices implemented in other languages, and then a standard for some library isn't useful anyway. And lastly, there is resilience. So if one microservice crashes, the others should not, should still continue to operate, probably with a reduced service. Otherwise, your whole system will eventually crash, and that's not what you want. So those are the 9 ISO principles, and what you can tell from these principles, and that's what I am going to talk about, the important technical decisions are not about how you implement your microservices, quite the opposite. That's the advantage of microservices. You can have different technologies in each microservice, so if there is a new technology that is much better than the old ones, just use it. But the important technical decision is, how do you integrate your system and how do they communicate? And basically, microservices are therefore extremely decoupled modules. If one of those modules crashes, you don't care because they are resilient. If you want to deploy one of those modules, just go ahead. They can be independently deployed. If you want to make some technical decision, well, not a problem, because each microservice can have different technologies, so you can make different technology decisions. So it's taking decoupling as a fundamental principle of modules to the extreme. So I would argue you should be using microservices if they are the simplest solution, and that is when the operational complexity is less, the additional operational complexity is less than all the benefits you get from the decoupling concerning deployment, free choice of technology, and crashes, and so on and so on. So this is why I think microservices are valuable. This is why how I think microservices should be defined. And this is also why I am going to talk about integration technologies and methods to set up a system with different types of integrations for the rest of the presentation. So how would you actually integrate microservices? Well, a very simple way is to integrate them on the UI level. So I could have some product search, and that product search could present a web page, and on the web page it could give links to some product detail page, and that could be done by different microservices. And it's just links, so I don't really care how the product detail service works, it's just a link. It could even return a PDF file if they want to, and they are free to do whatever they want, so they are really decoupled. Or we could have synchronous communication with REST, for example, or we could have some asynchronous communication. And this is what I'm going to talk about. So I am going to talk about how you integrate services using links, how to integrate them using synchronous and asynchronous needs. So let's start off by talking about front-end integration. How do you do that? Well, there is a very simple way, which is there is the system, there is the other system, and there is a link. That's fundamentally what I've just been talking about. You might want to do it a little bit more sophisticated, so you can have redirection. So I have a link again, I click on that link, I go to the other system, and then I'm redirected to the original system. This is, for example, what you also see in authentications on the internet. So on the OAuth flow that you use if you log into some site using your Google account, that's what you do there. You click on the link, it goes to Google, and then you log in, and then you're redirected to the original site.
That's basically what it is. More advanced would be the dynamic inclusion of some content into the website of another system. So here is my system, here's the other system, and here is the transcluded content. This is a very interesting subject, so there are many different ways how you can do that. Very simple way is to do that just using JavaScript. You can have server-side means to do that as well. So, for example, in my book I talk about ESI, edge-side includes. There are server-side includes to do the same thing. So there are quite a few ways that you can do that. And there's a blog by a few of my colleagues, by one of my colleagues actually, Till, and he talks about different ways to do that transclusion. So before I talk about this in a lot of detail, I would rather want to show you an example, and that's Crimson Insurance. And the reason why I like this example is because it's an insurance application, so it's not like all those applications that you're probably used to with some fancy website. I do apologize for the system being in German. So let's see, we can search for some customers. So in our case, it's Markus Müller, a typical German name. So let's take this guy and take a look at what he has. Well, he has been talking to us via the telephone. He's married to some lady, and he has 3 cars. So we can go to this car, and we can just write a letter about this. So we can have some letter that we want to write, or we can add a claim or a damage. So we could say, yeah, I did crash that car, and if I can enter some text here. And I can go back even further and go to the post box, which is right here, and take a look at all the nice things that I have here. This system is based on Docker. So what do you think? How many Docker containers are there in this system? So any idea? Any guesses? 10. 10. In the back? 5. Anything else? 50. Because the proper microservices system has 50 Docker containers, right? Okay. Well, it's actually where we can. You could have noticed if you took very close notice what's going on here. So we start off by looking at port 3000. So each Docker container actually runs on a different port of my machine. So this is the first one, so it's number 1. So I go to this guy, Müller. We are still at 3000. I go to his car, still 3000. I go to the letter, that's 3002, so that's number 2. And then we have the damage, so that is 3003, so that's number 3. And finally, we have the postbox over here, and that is number 4. And there is one that you didn't see, which is the share backend. So it's actually 5 Docker containers. So 5 is the correct number. Congrats. So let's take a look at how we did the integration here. And that's the other reason why I like this so much. So if we go to the car over here, and we want to know what this is actually, well, we can take a look at the source code, and we can take a look at how this thing for entering a claim or some damage how this is implemented. And it turns out that this is just a link, as you can see here. So this is just a link. That's it. This is how the systems are integrated. And if we go back to if we go here and we actually do enter a claim, then we are redirected to the original page. So this is the redirection, right? What we did here is we entered some information. This one went to 3003 to the damage application, and that one forwarded us to 3000 and said, here is the damage. It has been entered into the system, and that is because there is a success equals true in here. And oh, there is still one thing missing, so that's the puts box. And the puts box is a link, I think. Let me see, something is not working. It's not post box, it's prepress, of course. So there you go, it's a link. It's a special link because there is stuff in there like data-preview enabled and so on, and that's interpreted by some JavaScript code. So that's basically what it is. Yeah, so basically this is the third option. This is transclusion using JavaScript, which is again very trivial. It's a very simple concept. We've been doing that for ages. This is what Ajax is all about. So it's a very simple concept.
And the great thing about it is that the layout that you see here is largely implemented in the postbox. So as soon as you change the postbox code, you can change the presentation in here too.
And that's how that integration works in this place. Oh, and by the way, this is truly a system that includes a lot of different technologies. So it proves the point that it doesn't really matter which technologies you're using. So this one, as you can see here, it's a Spring application. This is the default icon of a Spring Boot application, while this one is a Node.js application. So those are two applications in two different programming languages, and they share the same look and feel, right? There is the same icon here. This one says new customer, this one says new message. So it is the same look and feel, but it's different because obviously a postbox should behave different from the typical front end. And this is basically what I'm talking about. So this is for systems largely independent because, or very decoupled because they basically just include links to one another. And from a technology perspective, it's really boring, right? I mean, there is some JavaScript code, and that's pretty much it, and links. And I do like that because I think boring technologies are less risky, so this is how you can build such a system. So this is what front-end integration could look like. And if you follow the links, you can actually run that system by yourself. So it's on my webpage, there's GitHub, on GitHub. And here's the explanation that shows how you can run it. And I have to admit it's a somewhat lengthy explanation. Here is the German translation for that one. But that is because I tried to figure out everything that could possibly go wrong and try to talk you through how you should do it. If you really want to start it, it's basically cloning the repository, creating the build by Docker Compose build, and then you can basically run the whole system. So it's in this example, it's 2 commands. Might be a little bit more in the other demos. Then you would need to do the build of the system itself, not just the Docker build. So it might be 3 or 4 commands, but that's basically it. And that's the intention with those demos. They should be really easy to run, and they should be an invitation to try more later on. So that's basically it for front-end integration. Here is, well, there's a blank screen. So here's the link to the demo on my GitHub page. It's also running on Heroku, so you could also try it on Heroku if you want to. You don't need to install it on your own machine. So that's one option, front-end integration. And again, I mean, another reason why I like this demo is because that's not the typical way how you think about microservices, right? There are a lot of people who say, well, microservices are really just REST microservices, but this is very different. It's basically web applications. And that's a very different way of implementing microservices. So much for the UI integration stuff. I think that's something that is often forgotten about, and that is why I put it at the very beginning of my presentation. So let's talk about the more standard case, which is synchronous REST microservices. It might be like the typical microservices that you find out in the world. Synchronous microservices, according to my definition, or to my understanding, basically means that I can talk to another microservice and wait for a reply while I'm processing a request. So I'm an invoice microservice. I am asked to show some invoice. So I get a request, HTTP request. I go to the customer service and say, please give me that information for that customer, for that invoice. I get a response, and then I send the response back. So while I work on a request, I actually do a request to another service, get the information, and put it back to the original caller. So there are challenges here. First of all, I need to figure out who to talk to. So where is that other service? So I need to have an IP address, I need to have a port in the case of REST. I should probably have load balancing, because if there might be more than one system that I need to talk to for resilience reasons. So if one of those systems crashes, I still get a response. And also because microservices should be independently scalable. And that's only possible if there is a load balancer between me and the microservice I talk to. Then there is routing. So probably I'm a huge system and incoming requests needs to be forwarded to one of the microservices. So I need to have some routing in place for calls that come from the outside. While load balancing is really about calls between microservices. And finally, if that system fails, the customer system, I must not fail. I must still present some information about that invoice. And actually, I'm not sure how I will implement that. So maybe there's something wrong with my architecture, because how should I present the information about an invoice if I don't get the information about the customer? I don't know. So maybe there is really something wrong, and I should really have that data in my service. So how could I implement a synchronous system? Well, one way of doing it is to use some framework. So in my examples are typically based on Spring Boot and Spring Cloud, but as I mentioned before, that doesn't really matter because it's just the implementation of the microservice. But I do need some solution around services covering all these other things.
And one of the important technologies that I'm going to use in this example is Consul. So here's the link to the example that I'm going to talk about. I'm not going to show it because, well, that's just going to take a little while, and I don't want to spend the time on it. So why would I use Consul for services coverage? That is in the core of this example. It's a system done by HashiCorp. Those are the guys who also did Vagrant for providing virtual machines to developers. It's written in Go, and it has a DNS interface. So if I want to talk to that customer service, I can basically do a DNS lookup for the host called customer, and Go could answer that request. And that's very simple. It's very technology independent. It's very well known. So maybe that's not that option. How do I do registrations? So there is no standard in DNS that says how you could add a new system to some DNS server. So there is a REST interface that allows you to do that in Consul. And you can also support configuration. So in Consul, you can store some values, and you can read values out of Consul so that your microservices are configured in some way or another. So it solves more challenges than I even wish for. It does more than just services cover. So that's great.
how do I register my services? Well, in case of Spring Cloud, there is an interface for console, and that's not very complicated. What I need is, I need a library to support console, I need some configuration. In the configuration, basically says, this is the console server that you need to talk to, and then a little bit some other stuff. And I need a few lines of code. I'm actually not sure whether that's true. I think it's more like one line of code, basically one annotation, and then you're done. So that really sounds like not too awful, because it's
just one line of code and a little bit of configuration, so it's less than 10 lines in total.
But I do believe that this is actually not such a bright idea, not so great, because it is a code dependency. It means that I do have code that depends on console. Now, why is that a challenge? It's not a challenge because I want to migrate to other systems. It's a challenge because it means when I use a different technology. So I understand that there are people out there who are not using Java, or even worse, who don't want to use Java. So what do they do if they want to provide microservices in the system? They would need to have their own library. It would be much better for them if they could just go ahead and wouldn't need to write any code. You wouldn't need to figure that out. Because then you have true technology independence, which is one of the benefits of microservices. So this is not hard to do, but still, it means that for other technologies there might be a challenge. So I will come back to that in a moment. For the time being, I want to talk about the routing. So if a request comes into one of those microservices, there is an HTTPD, an Apache HTTPD that forwards the request to either the order microservice, the customer microservice, or the catalog microservice. But how would I do that?
I mean, HTTPD doesn't have an interface to console, so it needs to figure out which services there are. Ideally, I should just have an additional service, put it in my system, and automatically the HTTPD would do some routing to that system. So if I have a new service over here, let's say it's an invoice service, I should have some request routed to that service without any additional configuration or anything.
And actually that is doable using console template. Console template is a technology that allows me to create a configuration file using a template. Huge surprise, that's probably why it's called console template. And it fills in some information from the service registry. And it can even restart the server. So what I do is I start console template, which is some process. Console template creates the configuration file for HTTPD, and it says, well, you know, here is the customer service, here is the order service, and here is the invoice service, and so on. And these are the IP addresses. So if one request comes in, please forward that to one of those IP addresses. And if there is a new service registered, that configuration file will be changed and the service will be restarted. So if you go to Apache HTTPD and ask Apache HTTP about what's going on, Apache HTTP would say, well, you know, there is a configuration file and there is data in there. And, you know, Apache HTTP would be fully unaware of the existence of console. It's just a configuration file. So that's actually quite nice.
So for this example, we are using, for service discovery, console, and we use the Spring Cloud library. For load balancing, I didn't talk about that, but what this example uses is the Ribbon library. Ribbon is part of the Netflix stack, and it's a very simple library that basically goes to console, gets all the information about all the service instances, and then does some load balancing on the client side. That's again, unfortunately,
a code dependency. So if we have someone who doesn't want to use Java, we would need to have some other means to do this. Routing, as I said, is Apache HTTPD plus console template, so that's great, and it just works. And Apache HTTPD is totally unaware of the existence of console, as I said. For resilience, I'm using Hystrix, which is sort of the standard library for resilience. But again, it's a library, and it's from the Netflix stack. So this is what is baked into what I'm using in that demo. For non-Java microservices, I would need to have some additional different libraries. And that's not the best thing, because it means that I would need to use different libraries, and I need to figure it out, and it's harder to use other technologies. So I do have a problem concerning that advantage of microservices. Maybe there are better options.
And it turns out there are, and in a way I already said that, but there is DNS. Console does have a DNS interface. So for lookup, I could just use DNS.
What about registration? That's still a topic. So here's again the link to the example, and this example is different because what this example does is it says if a Docker container starts, there's an event, and that event is intercepted by registrator. What does registrator do? Well, you can probably guess by the name, it does the registration on console. So it's a small tool that runs in a Docker container, talks to the Docker daemon, figures out whether a Docker container started, and then as soon as the Docker container started, it registers that Docker container in console. So there is no code used for registration. So if the other Docker container wants to talk to the first Docker container, it would do a DNS lookup on console and then talk to that other Docker container. And again, we don't have any code dependencies, it's just a DNS lookup. We just have to plug in the Docker DNS into the container so that the host resolution works. So in this case, we don't have any code dependencies on console. So to sum up, what this solution does is, for service discovery, it uses DNS
and registrator to register the Docker containers. For load balancing, well, actually console does load balancing because there is DNS, so you can do load balancing by DNS by returning different IP addresses for each lookup. So that's what this example uses for load balancing. And routing is still unchanged. For resilience, we still have the Hystrix library in our Java applications.
But apart from resilience, a non-Java microservice would just work out of the box. We would just put it in a Docker container, we would run that Docker container, and we are done. Because it would be registered using registrator, and for lookup, we would just have DNS lookups. So there is no code dependencies, no nothing. So those people who don't want to use Java, they should be quite happy about that solution. So that is why I think this is quite nice. So this is sort of tells the story that I am trying to tell in this presentation, in particular for synchronous microservices. What you want to aim for is a system where you don't have any code dependencies on the infrastructure, and that provides you most of these features basically for free. And there is one player missing in this field, and that is Kubernetes. Kubernetes, if you think about it, is actually a system that allows you to solve this problem. If I have a Docker container on just one single machine, and I crash that machine, all my Docker containers are gone. I'm not going to go into production with a system like that, because it's just not available enough or resilient enough. I just need to get that one server and switch that one off, and I'm done. The whole system, all the Docker containers will fail. So that is why you probably want to run your Docker containers in a cluster. So if one of the servers in the cluster fails, your system is still available. So you throw in a Docker container in Kubernetes, and it's somewhere in that cluster. And there is much more. So, and that is actually what I am going to talk about, because obviously we do need to have solutions around, service discovery and all these kinds of things. So before I talk about that in more detail, I want to get a few terms defined. First of all, there are pods.
Kubernetes runs pods. Well, that's weird because you just said it runs Docker containers, but it turns out that a pod is really just Docker containers that are very close friends. That's basically what they are. And they have shared volumes, so they can just share files, and they have shared pods. So if I am a Docker container in the pod and I go to localhost, some pod, I might go to my friend Docker container in the same pod without me noticing. So the idea here is if I have a microservice, there might be additional services. For example, to ship log files to some centralized infrastructure, to maybe do some proxying around HTTP requests. So maybe I have a proxy, maybe I have a system to ship log information to some centralized server, and the microservice plus those helpers, that would be a pod. And they would run on the same machine, they would share the ports, they would share the volumes, and that is quite nice and happy. Okay, so those are pods. Now the other term is replica sets, and replica sets are the result of a deployment. That's another Kubernetes term. So if I deploy something, what I actually do is I create a replica set, not a pod. And a replica set ensures that a certain number of pods run. So I can say, well, you know what? This is an important pod. Please do run 2 instances of that pod. And the replica set will say, yeah, I'm going to do that. Just trust me. And that is the foundation for load balancing and failover. It doesn't make a lot of sense to have load balancing and failover if you only have 1 instance of a pod. That's it, right? Okay. So we still need to have something to do to make that load balancing happen, and that is where services come in. So services ensure basically access to the pods. So there is a DNS entry. So I would say, please run that customer thing, and that would have a service called customer, and then I have a DNS entry called customer, and I have an IP address for that service. Not for pod. This is somewhat weird because you would think that each pod has its own IP address, right? I mean, that's what we're used to. But it turns out that Kubernetes does it differently, and if you have an IP address, that's actually for the service. So it might be more than 1 pod. Why would you do that? Because that way you can do load balancing on the IP level. So there is an IP address, and that would be load balanced across multiple pods. Why is this great? Because it means that it's done on the IP level, and there is no problem concerning DNS caching, for example. So you have very good control about which request goes to which pod, because it's all the same IP address, and you just need to figure out which pod the request should go to, and that is how what Kubernetes does for you. And there is more stuff, so there is a node pod. So the Kubernetes server would be called a node, and on each of these nodes I can have a pod. So I could say, well, the order microservice should be accessible on node pod 42. And if I go to one of those Kubernetes servers and I go to node port 42 on one of those Kubernetes servers, I end up at the order service, no matter which node, which Kubernetes server I go to. So this is how you can access that service from the outside. Or you can also have an external load balancer. So some Kubernetes implementations would provide the load balancer, and then I would go to that load balancer and say, here's a request, and it would be forwarded to one of the instances of order. So here's the diagram to make that well, maybe more obvious. So here's the deployment. The deployment creates a replica set. The replica set starts 2 pods. For example, 2 pods, it might be more, it might be less. And anytime I kill one of those pods, or one of those pods crashes, it starts a new one. And then I have a service, and that is where I have my DNS address, my class IP address, and my external load balancer. So this is how I would access those pods.
And that's basically how Kubernetes works in a nutshell and what you can do for microservices with Kubernetes. Here's again the link to the example. And if you think about it, that solves all our problems. So service discovery will be done using DNS. Technology independent, very simple. Load balancing is built in, it's on the IP level, so it solves that problem too, very elegantly and very simple. Routing would be done by the load balancer on the node pod that Kubernetes provisions. So I go to that load balancer or to that pod on any of my Kubernetes servers, Kubernetes nodes, and I would go to that service. There is still the resilience stuff, and I have to admit that in the example, I am still using the Hystrix library, but you could have a proxy. So you could have a proxy that says, if that service over there crashes, I do some stuff. Like, for example, I do a timeout so that the request is just stuck for a specific amount of time, not forever or not for a very long period of time, so that you can recover. If the timeout is too long, if that service over there doesn't answer, I might get stuck because I waited for that server forever. And then eventually my system would get stuck and I would fail. And a proxy could solve that. A proxy could say, well, I am in between those two systems, and I make sure that after a while there is an error and you can recover from that problem. Which is in a sense a weird idea, right? I mean, it means that we have something, the proxy in this case, that we access through the network, and it solves problems that we have because of the network.
Doesn't make a lot of sense. But it does make sense because if you have pods, you can have that proxy as part of your pod in a different container, and it would run on the very same machine. It would use the loop ones. So then you would be,
well, basically technology independent. You can just use any language that you wish. And that's how Kubernetes is a very, very important and very great technology for implementing microservices, because it solves just all of these problems and a lot more. I mean, I could go on about how you can do a lot of fancy stuff with Kubernetes. And the nice thing about it is it's even technology neutral. So I think it's great idea. So to conclude, you could use, to conclude concerning synchronous communication, I am still using the asynchronous communication. For the synchronous communication, console could be used without codependencies, but deployment is something that is not covered, which is a good and a bad thing. It means that you can run console with any environment that you want, even bare metal if you want to. And you don't need to install Kubernetes, so you can still run it on a classical environment. And Kubernetes is basically a very complete microservices environment that doesn't introduce any codependencies. So that's what this is about. So what about asynchronous microservices? Asynchronous microservices would say that I either do this, so if a request comes in, do this delivery, I send a request out, please do that invoice, but I don't wait for a response. I don't care when they are going to do the invoicing. It's just important that they eventually do it at one point, and that's all I care about. Or I do a spontaneous request. Give me all the customer data. Give me the new customer data. And then when a request comes into my service, please provide that invoice, I go to my local copy of my data and work from there. So those are the two options. And if I do this, if one of the other systems fail, I don't care. In this case, it would just be transferred later. I need to make sure that eventually the message is transferred, but it would just be transferred later if I can make sure that it's eventually transferred. In this case, well, it means that I get no new customer data for some time. I don't really care. It means that my data is outdated, but I can still operate. Usually, these systems can guarantee delivery, so that eventually those messages are actually transferred, and it's a great fit for events which are important concerning context and domain-driven design, so it is also something that is fancy or interesting concerning the architecture. There are some challenges, however, and that is primarily around inconsistencies. If I get the situation where one of the systems is down, then there will be inconsistencies because I don't get up-to-date information. It's basically a very simplified version of what Uwe was talking about, but that is basically what it is about. So that is basically it about asynchronous communication. So how could I implement that? Well, one way of implementing that would be to use some kind of message-oriented middleware, like for example Kafka. So let's talk about Kafka for a few slides. In Kafka, the information that you provide has a key, a value, and a timestamp. This is the information, so there is a record. The record has the key, a value, and a timestamp. So the key could be order 42, order 23, whatever. The key, the value would be the information that this order is actually made of, and there would be a timestamp when that order was sent. And if you send Kafka records around, you actually do that as part of a topic. Topics do have a name, and topics have records, as you can see on the right side, but they also have petitions. So here's a petition. Per petition, the order is guaranteed. So there is no out of order thing here. It's guaranteed. So that's great because it means that specific problems cannot occur. So there are no problems around records being delivered out of order, basically. If they are sent by the same provider, if they are part of the same partition. If I read some information, I just commit an offset. So, first message, yeah, I read that. Okay, so I commit offset 1. I get message 2, I get message 3, I get message 4, I commit offset 4. Then I've just committed all the other messages too, or the other records, I should say. 2, 3, and 4, because I committed 4.
So I commit the offset, and that is all the messages up to that point. There are consumer groups. Consumer groups mean that there is one consumer per partition. So I send out an invoice. I want to make sure that this invoice is processed only once, because it shouldn't be processed twice, because then double the amount is invoiced, and that's not, at least it's not a sustainable strategy to make more revenue. So, and I would do that using a consumer group. So I would have a consumer group for the invoices, and there would be one instance in that consumer group that is responsible for one of those invoices. So that's how that would work. And then my invoice would be processed once by that one system that is responsible for that part of the invoices. So that's roughly how this all works. We can take a look at that in more detail. So here's the topic, here's the record, here's the consumer, and here's the offset. It commits, as I said, it commits an offset for and not each record. So here's another record, and I could now commit this offset. So I've just committed another record, just one. I could have committed more than one. Here's another record, and this is all one petition. And if I have another petition, and I have another offset here, and I have another petition, and another offset here, those could go to another consumer. So I would have 2 consumers. So that would be a consumer group. And the first consumer is responsible for just one petition, the other one for 2 petitions. But each message goes to one consumer only, to one petition and to one consumer only.
either the left or the right one. And here's the producer. So that's a consumer group. So if you want to create an example, or the example that I've created is, I send out an order. I want to make it an invoice and a delivery. And that is basically what is happening in this example. Here is the link to the code. Here is what the system looks like on the
Docker container level. So there is an Apache HTTP. Because I just want to have one port for all the HTTP and HTML stuff. That can go to the 3 microservices. They each have the web UI, so you can enter orders, and you can look at them in shipping and invoicing. Order sends the orders to Kafka. Kafka uses Zookeeper to keep track of all the offsets, for example. And then Kafka sends it to shipping and invoicing. That's basically how it works. And all of these containers have the same, separated schemas in a common Postgres database. So that way they have their own domain model, they don't share any database schemas, and that is how this thing works.
How does that asynchronous microservice, or how do those asynchronous microservices
solve the challenges that we've been talking about concerning service discovery? Well, the way that we do it is we say, here's Kafka, here's the topic.
You're done. Because
that way the producer and the consumer are actually decoupled.
I don't send a message directly to one of the consumers. I just send it to the topic, and then the consumer will read it from that topic. So it's decoupled. It's much like straight service discovery for synchronous microservices. Load balancing is done by the petitions and the consumer groups, and it guarantees that each message is just delivered to one consumer. Resilience, well, if one of the services fails, the data will be in Kafka, and it will be eventually read. It's just that it takes a little while longer, so the latency increases. So I would argue that Kafka is actually a great technology, but I didn't talk about it. That's sort of a unique property or a unique feature that Kafka provides. It gives me access to old events, so I can even ask Kafka for very, very old events if I want to and if I have configured it correctly. So that way I can get an information about orders from last year or so if I want to. So that's something that is interesting. I have the guaranteed order. Also what I didn't talk about is I can have log compaction, so I can remove old information. So the idea is if I move from, I moved from Hamburg to Berlin and inside Berlin, so maybe I'm just interested in the last move that I did from my old apartment in Berlin to my new apartment in Berlin, because that gives me the most current address. Probably nobody cares about whether I've been living in Hamburg more than 10 years ago. And log compaction can just remove old records.
And the way it works is if there's more than one record with the same ID, just the latest record is kept. So that is how log compaction allows you to store data also in the long run, but to also compact it and throw away data that you don't care about too much anymore.
Consumer groups allow you to send records to just one consumer, so that's great. But that is the problem that I see here. There is additional infrastructure here, and it's not the easiest type of infrastructure that you could imagine, because there's persistence involved, so events are being stored, or records are being stored. There are petitions, there is replication, there are consistency issues, all these kinds of things.
So there are some challenges around that.
So we should look for alternatives. So here's an alternative. We could just use REST plus atom. Atom is the data format that we usually use for feeds, blogs, and podcasts, and so on. It is a data format that you can access through HTTP. And the idea is, if we can subscribe to a podcast, if we get new episodes of a podcast delivered through Atom in an HTTP feed, why can't we have that for orders too, or for any kind of domain objects that we might want, that we might have in our system? So why wouldn't we use Atom to do the very same thing for our customer data? It's very REST-like idea to use those web protocols and web ideas also for our systems. So how would that work? We would pull the feed, we would do an HTTP GET, give me all the orders, which seems to be somewhat weird, because if I want to send a message, it should probably be pushed to me, right? I just want to receive that message and work on it. Now I'm polling those messages. But the great thing about it is that the client is in control of the polling interval and when it polls. So it can just poll if there is nothing else to do. So it will never be overloaded. But it's still very inefficient. So I would get a lot of unchanged data. Give me all the orders. Well, here are 2 gigabytes of orders. Give me all the orders. Here are 2 gigabytes of orders. Let me take a look. No new information in there. Weird. That's not what I want to do. But HTTP does have some ways to solve that problem. So what I could do is I could get the feed. I would receive the data, and the server could send a last modified header. So it could say, well, this is the information from 10 o'clock. And the next time I send a GET, I would send an if modified since header, if modified since 10 o'clock, and the server might answer, well, 304, nothing has been modified. Or it would return new data. And what I could also do is I could, of course, page. I could say, just give me 10 orders, not all of them, or 100 or whatever. So that would make it more efficient. And that is what this example implemented. So if you look at it on the level of the involved Docker containers, in a way it's very similar. So we have order, shipping, and invoicing. We have the Postgres database with those 3 separate database schemas, and we have the Apache HTTPD load balancer, so that you can access all these 3 microservices from the same URL. The communication is different, right? So we do polling from invoicing and shipping to the order system. So there is an HTTP GET that is done there, and that is how those communicate. Now the interesting question is, do you even need Atom? Because the basic idea is that you get a list of all orders, plus a link to the details of those orders. And you could use content negotiation. Content negotiation is built into HTTP, and the idea is that I do a GET, and I say, well, I really want to have the order in that representation. So I could say, please provide it to me in the data format version 1.0, 1.1, 1.2, whatever. I could even say, well, do you have a PDF by any chance? So there are different ways, or there are different representations that I can have that way. And I have HTTP caching. There is really nothing that says that I need to use Atom. Providing a list of all orders, it's a very simple thing. If I just have a JSON document, that will be enough. A link is a very simple thing. I can have that in a JSON document, of course. Content negotiation is built into HTTP, as is HTTP caching, so I don't really need Atom. And the alternative would be to run my own format. And usually, I'm not a huge fan of inventing my own stuff, but in this case, it's so easy that I would probably do it, in particular because Atom has a lot of information, like author, for example, that really doesn't make a lot of sense if you talk about orders. It really does only make sense if you talk about blogs or podcasts. However, an Atom reader couldn't read your format then, but I don't really care.
The nice thing here is REST can be asynchronous. So it's not true that REST has to be synchronous all the time. It is something that can also be used to do asynchronous communication, and that's the point that I'm trying to make. And that is also why I was presenting this, because it can do a lot of stuff. I can have access to all the events, because that system over there that has all the orders, chances are it has all the orders ever since the Earth has been created, so maybe I can get all the old events too. There is a problem if I just want to have one customer or one consumer writing an invoice, for example. How do I do that? So I have 10 services, each of them is capable of writing invoices, each of them polls the atom feed. How would I figure out which one should write that invoice? That's very different from Kafka, right? In the Kafka case, I just send out a message to one of the receivers, and it's clear that that receiver is going to write the invoice. In the atom case, it's not so clear. So how do I solve that? By implementing idempotency. Idempotency means no matter how often I do it, the end result is the same. So the first system would say, for the feed, write an invoice. Do something in the database that says invoice has been written. The next system will say, pull the feed. Oh, here is a new order. Let me check whether I should write an invoice. No, there is some information in the database that says that invoice has already been written. And no matter how often I pull that feed, no matter how often I try to process that order, the result will always be the same. No more invoices are written as it should be. And the nice thing, so that's, by the way, I would think one of the drawbacks of this implementation means that I am ending up with a somewhat inefficient implementation because I need to check whether that invoice has been created, and it's probably not so great if you want to do load balancing and if you have a lot of systems that should write invoices, so maybe that's not too great. But the advantage is that you don't need to have any additional infrastructure. It's just HTTP, it's just REST, so there you go.
So concerning asynchronous systems, I would say the benefit is that the systems are resilient and decoupled. If the other system crashes, if it's not available, I don't really care.
The consistency is a problem. So I can easily end up in a situation where there is an invoice,
but there is no delivery or no shipment for some order, or the other way around. Did I tell you the story about that tablet that I ordered? So I ordered one tablet, I paid for one tablet, and I got two.
Nobody noticed, so maybe they followed this idea. In the case of Kafka, I can store all the messages. That is what sets it apart from the other messaging systems.
I can send messages to one receiver. In the case of Atom, it's an easier infrastructure.
So let me conclude.
I have to admit, I personally prefer decoupling and resilience over consistency. The hard challenges in a microservices system, in my opinion, is to decouple the systems, to make them truly independent, and to make them resilient. So if one system crashes, the other don't crash.
And I have to admit that the idea that an invoice is only created eventually and not immediately doesn't really scare me. I mean, if that takes a minute more or 2 minutes more or maybe half an hour more, should be okay. Of course, your cases might vary. So I would argue that in a typical system, might be different in your case, this is probably the trade-off that you want to make. So my priorities are UI integration, which give me resilience. If I just show the link, I don't care what the other system, whether the other system is running or not. I don't care at all. It's just a link, and as long as the user doesn't click on that link, I don't care. And if the user clicks on that link, it's the problem of the other microservice, not my problem.
So that's actually quite great. For asynchronous communication, the way that I think about it, if the other system crashes, well, my overall system becomes
inconsistent, but it still works.
So there is a sensible default. While for the synchronous system, I gave that example where I ask about
an invoice, and I get the data about the customer from the customer service, and then I answer the request, and I send out the invoice. So what do I do if I don't get the customer data? I have no idea, but I need to figure that out because that other system might not be available. So I would rather try to stay away from that case. If you found the presentation helpful, then you can send an email to this email address. I don't read emails to that email address, but you do get a response, so you will get a link to the slides. You will get the free primer and the recipes, and you will also get sample chapters from the Microservices book, from the practical Microservices for the continuous delivery book, and that's actually a microservice running on Amazon Lambda, so it's a small Python script that answers the emails. Thanks a lot for listening. Thanks a lot for staying here.
Are there any questions? Okay, so thanks again. I am going to stay here, so if there are any more questions, feel free to come to the front and ask them. Happy to answer any questions, and please do send an email if you want to get that information. Thank you. Thanks for staying here. Thanks for listening.
Yeah, so thank you for coming. You can stay here. There's fuel left, I guess, and food too. So talk to each other, share whatever you want. Thank you.
Thanks.